All right, in this video, we'll be exploring the relationship between intermolecular forces, IMFs, and some common physical properties. Now, if you watched the previous video, we went through the different types of intermolecular forces and the differences between them. And here we're going to actually start to apply those to try to look at some different kinds of physical properties. Now, the underlying thing that you have to know is that ultimately, the strength of the intermolecular forces is going to have a big impact on these properties. Stronger intermolecular forces are going to be harder to overcome than weaker ones. So whenever we're thinking about any kind of physical property, whether it's a phase change, whether it's any kind of solution kind of dynamic, the stronger the intermolecular forces are, the more that we're going to have to deal with them, and the more that they're going to have an impact on the overall property itself. So when I look at viscosity we can describe as the resistance to flow for a fluid. And what that means is, in general, that things that are more viscous are going to appear thicker. They're going to be harder to pour. And as a result, they're just going to be a little bit more sticky as a result. And so a good example of this is what's being shown in the panel here. A viscous liquid is going to have a lot more adhesion kinds of forces. It's going to stick together a lot better than less viscous liquids would. But the main factor, there are two, but the primary factor that we're going to look at is intermolecular force. When we have strong intermolecular forces, we're going to have more viscosity. And the reason for that is, again, if we think about flow, that's the ability for those molecules to start to separate from each other a little bit so that they can actually be poured. The stronger the forces are to each other, the more they're going to stick together, the less likely it is that they're actually going to flow. So stronger intermolecular forces are going to lead to greater viscosity. Now, the other factor that comes into this, and this is completely unrelated to intermolecular force, or at least less related, is that of temperature. When we increase the temperature, we are increasing the kinetic energy of those molecules that are holding it together. And by having higher kinetic energy, we're going to see more molecules separating from each other. We're going to see a decrease in viscosity. And that's the case whether we have polar molecules or nonpolar molecules. Either way, they're going to see a decrease in that viscosity as a result. Now, if we look at this by comparison, we can see that within our alkanes, so again, we're talking about substances here that are nonpolar, and so when we see nonpolar forces, we need to be thinking about LDF, London dispersion forces. That's going to be the primary intermolecular force between these nonpolar molecules. And what we can see is that with nonpolar molecules and with London dispersion forces, again, if you can recall from our previous video, there is a direct relationship between the strength of those forces and the molar mass. And so what we see is that as our molar mass increases, our London dispersion forces increase, and we see an increase in viscosity as a result of that. The next physical property that we're going to look at is vapor pressure. Now, vapor pressure is the measurement of how much a liquid is evaporating at a particular temperature. And the real simple way of thinking about this is that the more things evaporate, the higher the vapor pressure is going to be. And so there's some temperature effects involved there. We know that when temperature is increased, we're going to see higher rates of evaporation, which means we're going to see higher vapor pressures as well. Now, there is a certain point where the substance's vapor pressure, that is how much pressure is exerted on the surroundings by the liquid that has evaporated, when that pressure of evaporation equals the atmospheric pressure pushing down on the liquid, what we reach is a particular point in the substance's lifetime that we call its boiling point. So boiling point is just the pressure, the temperature point where the vapor pressure of the liquid matches the atmospheric pressure of the atmosphere, and those two exist at the same time, and we end up getting boiling as a result. So what does this have to do with intermolecular forces? Well, what we can see is that we know that intermolecular forces will impact vapor pressure and boiling point very, very similarly. Now, we don't have groups here, so let's kind of skip ahead to the next part here and talk about how do we know what the relationship actually is. Well, if my intermolecular forces are strong, keep in mind we said already that strong intermolecular forces mean that the molecules are going to stick together more. Well, if they're sticking together more with strong intermolecular forces, that also means that they are going to be less likely to be separated. And since evaporation is going to be the separation of molecules from the liquid phase to go up into the gas phase, strong intermolecular forces are going to affect vapor pressure in a negative kind of way, meaning when I have stronger intermolecular forces, I'm going to have lower vapor pressures. Now, since vapor pressure and boiling point are kind of inversely related to each other as well, meaning if I have a low vapor pressure, I'm going to need more energy, higher temperatures to get that vapor pressure up to atmospheric pressure. Having a low vapor pressure at, say, room temperature means I'm going to have a pretty significant boiling point once I get that substance up to the atmospheric pressure. So, in summary, if I look at my intermolecular forces, if my intermolecular forces are good, what I will see is a decrease in vapor pressure and an increase in boiling point. And obviously vice versa. If my intermolecular forces are weak, my vapor pressures will be high and my boiling points will be low. Now, this particular graph represents an interesting kind of trend, because what we can see is this is the boiling points for a series of molecular substances, starting down here with the methane, CH4, and rising all the way up to water, H2O. And these are all hydrides. So these are all hydrogen compounds mixed with other nonmetals to make molecular covalent compounds. So nothing in here is ionic. Nothing in here is really routinely special other than that aspect, other than the fact that we have hydrogen covalently bonded to nonmetals of some kind. Now, what's interesting here is there are two zones that we can kind of look at. The first zone here is pretty well behaved and well managed for all of them. They all see a general trend where my molecular mass is increasing, and so is the boiling point. And it's happening in a very linear fashion. And the reason for that is that the primary force that's changing these is London dispersion forces. London dispersion forces are what are driving this particular change to occur. And since we are seeing increases in molar mass, we are seeing modest increases in molecular weight, we're seeing modest increases in intermolecular force, and we see modest increases in boiling point as well. What's interesting about this particular graph, though, isn't this part, but actually this part. We can see that the methane, CH4, is following the same kind of trend. We have low molecular weight here, we have higher molecular weights here, we see a general linear trend in the group 14 hydrides. Why don't we see that same trend among the group 15, 16, 17 hydrides? Well, you might be thinking, well, that's polarity. Well, the problem with that line of reasoning is that polarity plays into the roles here as well, but we don't see nearly as drastic of an impact. The real reason has everything to do with hydrogen bonding. Think back to our definition of hydrogen bonding. We have to have polar molecules that either have a hydrogen to fluorine, hydrogen to oxygen, or hydrogen to nitrogen bond. all three of these compounds have those. So the reason for their big uptick here, the reason their boiling points are so incredibly high compared to other similarly molar massed substances, has everything to do with that type of force. The hydrogen bond is a considerably stronger intermolecular force than even polar bonding down here. And as a result, we see a massive increase in boiling point relative to where we would expect it if it was on trend like the methane is. And so just to kind of recap, stronger intermolecular forces will lead to lower vapor pressures. And the reason why is that these intermolecular forces are keeping the molecules close together. And so the stronger the forces are, the less likely they are to vaporize. The less they vaporize, the less pressure they're going to exert on their surroundings. The last piece that we want to look at is solubility. What determines what dissolves in what? Now, a little bit of terminology that goes along with this. Solvent and solute. Solvent is basically the substance that does the dissolving. Solute is the substance that is dissolved in the solvent. Easiest way to think about it, solvent is the stuff that's there in the biggest amount. Solute is just everything else. And there can be multiple solutes in one solvent. So it's possible that in an aqueous solution, you can have multiple salts and sugars and other things dissolved in it. If we didn't, then the beverage industry as we know it wouldn't exist. Now, the other component here, the other term that we need to be aware of here is solubility. Now, solubility gets thrown around in a number of different ways, but our definition here is going to be the maximum amount of solute that can dissolve in a given amount of solution. Usually this value for solubility is expressed in grams of solute per 100 milliliters or 100 grams of water, or whatever the solvent is. So that's usually, we express solubility in terms of grams per 100. Now, in terms of solubility trends, what we know is that strength and number of interactions ultimately are going to determine solubility. The primary thing that we're going to look at, the primary force that we can think of, is this concept right here. And if you haven't heard it before, you'll hear it several times throughout your chemistry career. Like dissolves like. Now, what does that mean? Well, that means that substances that are polar or ionic, things that have charges, whether they are partial or complete, are going to dissolve in other things that are similar. And things that do not have charges or have very limited charges, like things that are nonpolar, like things that have induced dipoles, these are going to tend to stay together. Hydrophobic things tend to dissolve in other hydrophobic things. Hydrophilic things tend to dissolve in other hydrophilic things. If I take something that is nonpolar and put it in with something that is polar, the polar things will basically squeeze out the nonpolar things. Yes, we might get some limited amount of solubility. Previous slide talks about oxygen and its slight solubility in water because of a dipole distortion that is created by the water on the oxygen. But that is pretty limited, and oxygen is really limited in its solubility in water. But this is the overall force. This is the overall trend that we're looking at. And so in our next video, we will take a look at phase diagrams. And this will be the last video out of this particular subset on intermolecular forces. See you next time.